You are all very welcome. This here is another webinar from the channel TURBIVAP. We came here today to talk a little. The theme of today's live here is a summary that is a summary. We want to do it here. Not everyone who works with a thermal plant and who knows about steam turbines, and not all people they also want to know more in depth. So that's the intention of this one. And for those who want to get closer somehow certain form of turbines, gives a very general overview for these people, and no very general concepts, even rude. Obviously the name resume is already here. So we're not going to go into anything in depth, okay? It's really superficial, okay? But again, as an idea of spending of a message to bring people to learn more about turbines, okay? Then I will pass here some topics here. Let's take a look, okay? So what do we have here? What is the summary? The goals. Ours is to have a good time general. So what is a steam turbine? What is it for? How does it work? And the main types of steam turbines. It's okay. So let's go. It's going to be really quick. As the name itself says, my goal. That my mission is for the person to stay. A very concise webinar is very quick, very brief. In fact, for those who are just wondering superficial, there it is. There's an overview there at the beginning, middle and end. Yet well, very briefly, to have someone if you want to leave questions, then leave it at the end, and then we come back. The channel already has a lot. Talking about steam turbines who wants to become a specialist and go deeper into the topic, okay, but that won't be the focus today here, obviously, because you want just know, well, roughly, gross beauty. So what I say is superficial. So let's go. First, just talking a little here. We are a consultancy company, steam turbines, with innovation and agility. We can help with consultancy, face-to-face, digital training, modernization service, projects focused on turbines, technical supplies, the entire feasibility study part. Okay, then just get in touch with us there. We can help you with this, okay? My name is Ronaldo Pyers, for those who don't know me yet, okay? We have a whole part 2 of equalization of proposals, technical support. In short, we need something related to turbines. Contact, that's where we help you. If we don't help, we do you know who can best help. It's okay. So come on, let's get started. Steam turbines indeed. What is a turbine? In a very general way, let's take a look there. It is logical that I believe you are here. You may already know a little about them, but it is a machine that transforms the thermal energy of pressurized steam in mechanical work. And this is the main function of the turbine steam. She will always be working with steam at high pressure. More or less, but always at high pressure. And for what is the use of what would be ours, or our other approach to doing it? Let me just pull this one out a little bit square, so as not to disturb us here. Well, steam turbines are widely used for generating electrical energy, whether for activating equipment, industrial, process, or for driving an electric generator. So, logically, whenever you have a thermal plant, where there is the presence of steam, that our fuel is steam, we can obviously have the application of turbines. So it could be to trigger from a generator, which is the pure generation that we call to activate an electric generator, even for power generation, even for mechanical drives. Then we are talking, for example, pumps, mills, blowers, chipper, fan, and anything that is mechanically driven. That there is no electrical generation properly speaking. And we'll see why that is, right? Some reasons for that, including the main types of turbines for each type of application. So far it's been calm. We've already gone straight to the point. I believe there should be no doubts. So whoever wants to send it there a message in the chat. There's the video. Nice, okay. If the audio is good, if you have any questions, we then try to do a session here alone for you to be aware. This webinar here today is being a slightly different format. It is being a closed webinar. Then we'll see if we publish it or not. The idea is to bring people here too to participate in this way. With us it's more intimate, let's say so. Perhaps it becomes more restricted, but there is time to give a little more attention, a little more calm and so on. So let's stop talking lenga and let's continue here. It's going to be really quick today. Okay guys, and as a summary, there's no point in staying here. Here I am talking about turbine steam, right? So I believe you want to come here, know our topics there. What it is and what it is for. What types, and finally. Now let's make it a little better in that first definition we made on her. Saying that she is a screen equipment, a device, a machine that works with steam pressurized, which converts this vapor in mechanical work, right? But let's understand a little now. But technically then the steam turbine, she is a driving machine. Because it is a driving machine, right? We always have a driving machine. One moved, one engine. One moved, a driving force. A driven one, in short. one driven, one dreamer. So she is a driving force. She's the one who triggers it. Okay. She is the main equipment for the drive. So it is she who will transform the energy real potential of that steam pressurized that we have ever seen in energy kinetic, which is the speed is associated with speed. And this she in turn, she is transformed in mechanical rotational energy mechanical work there on the output shaft, on the turbine shaft. So here we start to enter a little more in detail. It's good that she transforms. Here we are already seeing that there is 3 basic types of transformations. The first, which is the transformation of energy steam potential pressurized into kinetic energy. The first, then kinetic energy. It will trigger the generation. Kinetic energy generates in mechanical energy of shaft rotation. The steam speed will rotate the turbine rotor, and this in turn transforms this mechanical energy and electrical energy through rotation of the turbine shaft, which is connected to the generator rotor, or that of the driven machine, and then again the same equipment. Okay, then go. Now it will start to get a little clearer, just so we don't skip this here, right? More like conceptual, a brief history here, very brief indeed, something more historical in the sense of not having so many references thus. Although some literature still and date back to the much earlier period okay. But the fact is that the first reports there of turbine application steam was by this scientist, right? Architect. You will find some places there Giovan Branco which has the first reports there. Yeah, it was used. It is not yet known how to feed pilots something like that. So basically here was a device which was fed with water and fire beneath it, and then a jet of steam was projected. It was a wheel and was already doing some work mechanics. So as not to know for sure if it was just one thing. One curiosity, a toy, or if in fact already had some application for work. Let's say it like this, right? Before that it was still only as a historical concept. There are also reports still there at the time, before Christ there was. It's already a device called I read that it was a ball even brass, copper. No one knows for sure which was fed with water, and then taken to the fire to also make this rotation movement. Not knowing for sure if it was something more optics. A thing for the gods from that time or something like that. Yes, but there are reports out there leaving this part there a little longer mysterious aside, and coming from more effective things. It was there around that the engineer Gustavo de Laval. Many people have heard of him. He did it there. He built the first turbine steam indeed, and making a wheel rotate through jet directing of steam at high speed. Already in assembled reeds on the periphery of a wheel of lava, so it was a precursor. Their so created so-called first internship. How will we see, right? So there it was already a more industrialized thing. Let's say it like this, where it all really began. And then it was around that in fact, another engineer. This time a French engineer, Auguste Rado, he introduced a little more turbine. Go with several groups, not this time a single one like the one in Laval. This one has already done several stages, let's say, of different levels and different sets of wheels. What would it be like the steam expansion device? What are we going to see soon? But then he already started to do what was only one. He's already done this series and making it like this Laval turbine assembled in series within the same housing. Okay, so we'll see some other names later. It's just like a general concept for you. So, do you understand? Over time, a lot of things were being modified, altered, and efficiency gains were substantially increased and is today. Sometimes we saw turbines very big in the past. Today although there are still large turbines, but each time they are reduced. In contrast, their deficiencies are increased. So today work is focused on changing efficiencies. So come on, let's get started a little deeper there in the energy of the thing, right? In the engineering behind the process. So, with the turbines, let me just pull it here so as not to disturb us here too. So, but how does it work? A turbine, all good, it transforms heat into work. We transform energy of the pressurized steam there. The thermal energy of that steam there in mechanical work. But how does this happen, right? As I already made an advance back there. That works next the turbine it receives heat from a hot source. In this case, we are talking always from a boiler. She gets the job done in the expansion process of the turbine, which we will see a little deeper. Then it expands this vapor, and then she rejects this heat received there to a cold spring, which would be the condenser. It actually rejects some of that heat, and then return to the initial state, completing the cycle, and then more steam is returning, and the condensate is already returning, commonly known as water. So it's a little bit of the process that in fact We're going to take a look at it now. Basically it works like this. This here is the cycle that involves the operation of the entire turbine steam, the so-called Rankine cycle. But the scholar is a physicist, a chemist who invented this. Who studied, dedicated his life studies to this. That's where you receive it. The name Rankine is the same as his name, okay? So it's basically a closed cycle. Although obviously process losses occur in terms of efficiency and everything else. And no process other than cycles theorists. This is a practical cycle. The Rankine cycle, the technical cycle we have too. The theorist would be the cycle of Carnot. But then it would not be very applicable. Because then it would be, as the name says, is a theoretical cycle such that we are talking about a practical cycle. So the cycle goes through these steps, these 4 steps, which would be what basically here, starting here with 1. Here we have water pumping any. Okay, we're getting it from somewhere, some reservoir. For us, it doesn't matter. At that time we're doing a pumping. We're taking this one. We are already dedicating some energy in this fluid here. We are playing there for boiler. The boiler has an inlet enthalpy in enthalpy. When we talk, we are speaking in relation to temperature. Is the energy potential of energy. Even entering the boiler, we will add heat, a bit of input here. So we're becoming hot and that fluid there will be an output that will enter the item 3 here, which is our turbine itself, will expand within the turbine steam. This steam will be expanded, will look a little deeper. What is expansion about? Okay. And then it will generate work outlet on the turbine shaft. It's okay. And then this steam, after passing through the turbine through all stages of the turbine, it will be extracted. It will be taken away. It's going to come out. Come out of this turbine. Will be output here to the condenser. Will be collected there by the collector, the condenser. So here is different from what happens here. Here we have a calorie temperature withdrawal. So we are withdrawing calorie of the vapor fluid to transform it in water and liquid again. And for the process to renew itself. That's it. Maintain the thermal Rankine cycle. Here is another view, is a diagram of temperature as a function of entropy, showing these steps. This one here, the water saturation curve. So here we have everything that's below that line that is considered liquid or liquid plus gas. How are we not going to see it today, right? But it would be. And above that line here we are talking about steam. So here, leave the position 1 for pump and pump to boiler. 1 calorie of fluid is added, then the process goes until the expansion of the turbine. Here we have the region of superheating of the steam. For those who don't know, there are the turbines, they rotate using superheated steam, and then here it is done turbine expansion. The enthalpy is then removed, the calorific value of the steam, and is transformed into output work, not on the turbine rotor. Beauty. So this is the Rankine thermal cycle, just like this one here for Rankine. It is for the steam turbine cycle, the Britten cycle, which is another thermal cycle is aimed at gas turbines. The diesel cycle, use of combustion engines. Each one has a specific cycle. This is the Rankine cycle applied to steam turbines. This here it's a little more detailed. It's the same cycle, is a little more with the cube already, with more realistic in relation to installation there of a conventional thermal plant. Okay, so we have the same peripherals with addition of something a little more detail about the bombs. Okay, here the turbine, here we are adding a reducer here in case up to megaturbines. And it is very common, a reducer more or less. Then the reducer starts to lose a little efficiency of hindering the process. Then it is no longer used. And so, basically that's it. It's the same process. The boiler here will do the heating. Throw it at the turbine. The turbine expands the steam. The reducer makes the reduction of this output shaft speed, give a torque here to throw it to the generator, the cooling tower. To mean, the steam leaves here through the condenser. The hot water goes there to cooling towers, cool the bomb. Throw it in the tank again, and then the process is renewed a little more peripheral here. As you can see, beauty. Let's look at some more things here. So now like this, let's get into the part a little bit now of the types of related nomenclatures with turbines. So basically there are turbines, air engineering. The concept behind a turbine, he might be the type action or reaction turbine. Let's go slowly stop to understand this a little. This is quite conceptual, right? The expansion of steam in the expander, it causes high speed, producing force on the mounted reeds on the periphery of the wheel. So basically the steam is being directed against the profile aerodynamic of a reed, and this reed, then it receives this vapor pressure, and transmitting the rotational movement of the shaft. If you look at the graph here, the downward velocity of the steam in this type of turbine of this project, in this concept of this project. In this design of action turbine, the steam velocity when passing through the wheel vane of the wheel mobile. Here we are always talking the speed of the steam decreases, however, the pressure remains stable, so it doesn't happen a significant pressure drop, although it still occurs, but it is very marginal. It is even negligible, disregarded for study purposes. So, a turbine of action, she has these characteristics, whereas a reaction turbine the expansion of steam in the expander and causes high speed too, just like the action turbine, producing force on the reeds mounted on the periphery of the wheel. Until here nothing changes with the fact that the expansion of the reeds it causes a reaction force. So, in this case of reaction turbines, what happens is that the moving reed itself it also ends up expanding the steam that is being directed at her. So in that case, we also have, just like here, the speed when passing the wheel vane mobile. The steam velocity is decreased, vapor pressure also decreases. So, that steam there it will also happen a drop in pressure also in the wheel. So it would be a practical effect that people often use to stop to give you a little insight into this concept. That's a bladder. Imagine yourself with a full bladder. You catch her pet there and release her. So, just like in action, play the bladder forward, the air coming out, the reaction. She is also doing work towards conversely, finishing this expansion too, okay? So that's what changes the design of the project. An action turbine for a reaction turbine in reaction to vapor expansion. It occurs both in the static part that we will see a little further ahead, as well as the moving part that the reed moves. In action, expansion does not occur. It only occurs there. In the stationary element stationary, on the expander, that's why pressure doesn't occur here in the circle, and here it already occurs in the reaction phase. Are you explaining calmly? Leave it in the comment for us, so we know if it's going to be cool. Otherwise we'll come back here and forward. Many people create doubts. Tell it like this, physically. You looking at a turbine closed, for example. It's hard for you to know, right? There's no way to know. Now, if you see in the visual there, then you start to decipher this type of action or reaction, not because obviously of these aspects here that I am mentioning it, but rather for the look due to the constructive characteristics which we will see soon. Okay, so, before we go into more details here, just see if here is a little animation. Let's take a look a little bit in the process. How is this happening here? It's just another illustration. I don't know why it is, it's not running, but that's it. Here the expansion is taking place moving elements, which are the wheels and static ones, which are fragments or fixed reeds. We're going to see a little bit details later. Okay, but that's it. He's expanding the steam high temperature. So much so that it's redder here, let alone towards the end of the turbine. The steam gets colder, lower temperature, lower pressure. It's there, then we'll be seeing here. Oh my god, wait, are you going to come back here? Geez, much more it's been here. Let's come back here. This one goes now. I think it has to stop here. So what happens here? Here we have the hot part called the hot part of the turbine. This is the cold part, right? Because the steam here is on the block, is the control block. So all the steam comes from the pipe there at your plant. He comes here for this by a flange pipe. All high pressure steam that comes out of the boiler will go through elements here static, right? Safety valves. Well, no, I'll go into detail. It's just a summary. And then it enters the control block here, and here does the admission control how much steam that will enter the turbine. But here we have the hot, loud part pressure, and here it is cold, low pressure. Then the steam comes in, goes meandering between moving and stationary wheels, and continues to expand. What is expansion? Imagine that steam at a given pressure and temperature bigger. It takes up space, a smaller volume. So, if the vapor pressure decreases and its temperature too, what happens to the person? With the volume, it increases the steam. It occupies much less volume than water, for example. Right then it's about 1 to times there the fraction of that there. So, as the steam goes losing pressure and its temperature, it increases its volume. That's why the wheels, the reeds of the last stages of the turbine, it will be increasing over time of the turbine, from inlet to outlet, precisely for this due to this characteristic of steam to accommodate this expansion of steam. So I hope it's clear here the concept of expansion, because we always will talk about expansion. The expanded steam, the diaphragm expands the vapor, and precisely because of this characteristic. So that's what it's showing here. The steam is expanding there, and here it is showing another view. Then it passes through the diaphragm or fixed reed. This element here is static. This is static. This static is here the rotor vane wheel, which is the only moving element that is rotating. So, if you notice this profile here, what happens? It has an aerodynamic profile here, it's not for nothing. He has a restriction in passing. It has a spring, a smaller area here, a larger area here. So we're forcing this steam here gaining speed. Because we are restricting. We decreases pressure and increases speed. This is it. What happens inside, that's why we talk, expand, and then here it has an aerodynamic profile. These parts are well polished, the surface finish to have less contact, drag possible to increase efficiency, and other features too. But let's speed up here, which is a summary. We are not here to enter a lot of detail. Okay, but that's it. Then the steam meanders, it goes by, it goes around, and leaves and another steam comes, the pressure will drop, and the temperature will drop, and then the process it's going to be continuous. It's going to be fed, the steam is renewed. This one is basically the working principle. Here we have a little bit. Another condition here we have here representation of moment zero. Since the static rotor is at rest. Absolute. Then the steam will hit the profile of this reed there, and it won't turn. Nothing will happen until this force, this pressure. It is enough to win all rotor inertia. And then we go to the second condition that will start at some given moment, moving that rotor. Then it will begin to rotate the turbine shaft. Then we will reach the maximum condition efficiency, which is when this dam it's hard. It won't help that the train it's a lot of technology. Man. Oh, what a shame you're not. That's how we are live. Wait a minute, put it on. Son of God. It's actually I'm not seeing it here. Well, this is how far we've come, stop here. What's going on here? So here we have already seen moment zero, he's resting here. He's starting to walk. So some of this steam here. He's representing here that he is moving. He's stopping a little early. Here the steam passes, does nothing. Here he starts to walk, right. And here the maximum efficiency. And it will be maximum efficiency exactly when this speed is of the steam jet. It is half the rotation speed. From the axis we will see a little more in another graph that I will show now here, if possible. So let's play here. Oh damn. Did you see that I'm not much of a technology person? Right guys, I'm not going this way so as not to lose the thread. So what happens then? We have this condition here. Imagine the profile of a reed. It has a circular profile, generally symmetrical or non-aerodynamic. We won't go in lots of details about it here, but he has a profile that is lightning, a semicircle. Imagine then what happens, the rotor, the steam. It is being targeted on this profile internally in the reed pressure area. The pressure is the outside suction part. So this steam is being directed in this reed profile on this profile here. And this here is representing exactly the internal profile of the reed. It's this one. So this one we already have here an instruction here, a reference, which is the graph of work. And this here is the graph regarding strength. So here is the reed speed divided by the velocity of the steam jet. So it goes from 0 to 1. Okay, so it will be progressive reed work. As he enters here, he is reaching a given the work decreases by smaller that it is at the entrance to the reed. But he hasn't arrived yet at the point of maximum reed efficiency, which is precisely that incidence almost degrees. Let's say like this perpendicularly. So this steam is being projected. This pallet is being moved tangentially as it arrives up to the semicircle profile here of the reed, which is exactly here at half the speed of the steam jet here, where we let's get the most out of this reed. And then it starts to reduce? Okay. That's what happens now. Here we have the force graph. Then it starts progressive. It goes. Unlike work, strength. He is only growing until this steam exit the reed profile. Okay, let's comment guys. If you have any doubts. There are, it's cool. The concept is getting cool. So this is the secret behind the thing, okay? And where does the magic occur there? But let's keep talking a little more about the details. Okay, here we are going to talk now, because of the characteristics, then we talk. Remember what we saw there, which has two types of concepts, turbine design concepts, the action turbines and reaction turbines, that in action turbines expansion occurs only on static element and reaction. The rotor blade also helps. She finishes expanding the steam. That's where we have some features of each kill the action turbines. They feature a wheel configuration and axle disc formats, but wheels. This axis can be mounted by interference. It can be a monoblock shaft, what we call a monoblock rotor. It is a single forged and machined piece, but it's always will have wheel features and disc formats. And then we will compare with the other. And it will be clear to you the reeds. They are mounted on the periphery of the wheel, as you are seeing here. This one is a type of turbine which has lower axial thrust, precisely because he is not by the rotor, which is the moving part. They're the movable rotor blades. She didn't finish to expand the steam as well as in the direction. This results in lower axial thrust. The design uses diaphragms. What are the elements that go before the wheels, that project, and which are? which are designed with the function to give a speed gain in the steam flow in the steam jet, directing against the reed. So the steam is coming in here. He passes through the first, by the first expander here, passes the first row of wheels, and finds a set of diaphragms static, expands the steam and finds the second row of wheels, and so it goes. The process is a more simplified design. Turbines more the project, more financially, more economical, for presenting the least complexity of the project. Anyway, now let's make a comparison here with a reaction turbine. And you will start to become an expert there to decipher. If you see a part or a turbine open, then you will be able to decipher this type of information. A reaction turbine, it features a rotor in the shape of drums different from this one. So if you notice, it has a larger diameter. Okay, maybe there is a central axis and the drums, even though they are assembled into blocks, are configured, the rotor is being assembled. So in this case the reeds that are written wrong here, they are mounted on the periphery of the shaft, different from the action which is to mount on the periphery of the wheel. So this here is the axis. If you notice, we have here from this radius of this axis surface up to the surface here from the wheel. We have a distance here axial large radial distance. Let's put it this way. Here it is much smaller. It's a small radial distance. So he requires better internal sealing control. Here generally there are sealing blades between one element and another. Here it is no longer so mandatory that has just to improve this issue of reed reaction. The design of the project uses fixed reeds and reeds furniture. Reeds with lower radial height, like I said. So here, unlike here, they are not diaphragms assembled. They are fixed reeds. Also is a reed with a smaller height, the radial of directing the flow to the rotor. So basically, conceptually, these are the differences between an action turbine and a reaction turbine. So look, there are records with large radial height, with discs, rotor mounted with interference, has diaphragms, reeds with passage area of larger vapors there in the last stages. So we are talking of an action turbine. Okay, instead, he looked at her. There was a drum there, format postponed, with small reeds and fixed reeds instead of diaphragms. There we are talking about a reaction turbine. Reaction design. Okay, it's getting calm there until now. Send it in the chat, guys. Leave a message. I don't know this if the chat is open. I think so. I don't know if we left that blocked. Send if you can. Just test this, please. Let's go. I want to summarize. I don't want to waste time like this. Neither do I want to. I believe that whoever is here today, you want to be objective, okay? And we will try to be right there beyond this question of action and reaction. The turbine project, he has the types of stages, each has the internships, which is an internship. In fact, before we talk about these, the types of internship, the internship nothing more is than a stationary element to expand the steam, followed by a rotating element to absorb and transform this direction of rising steam speed, high pressure. So, this is an internship set of parts. A stationary part is a moving part, being the action turbine. As we saw, it will be a diaphragm is a row of rotor wheels, being a reaction turbine. It will be a fixed reed, and is also the movable blade of the rotor. This is an internship. Now, at this stage he can still introduce yourself like a Curtis or Mouse type. What do these names mean? Because besides being action-oriented, he could be Curtis or Raptor. Curtis is nothing more than the internship, the name of the inventor of that stage, Charles Gordon Kurtz. That guy's name, after the pronunciation Kurt is. But what is it? He's a wheel with double row of reeds, okay? Then, basically it is well applied in single stage turbines or in the first stages. Quite common, although there may also be, beyond the first stage in subsequent stages, also more than one short stage in the same turbine. That's what I want to say in short, but this is the Kurtz stage. He is his characteristic. It is a wheel with 2 rows of reeds. He is, although yes, there are 2 rows of reeds. It is considered an internship. It's a single wheel. So it's a wheel with double row of reeds. The wheel generally has to have, generally not. It must have a license plate steam redirector between these 2 rows of reeds, because imagine that we have the ranks of reeds, both reeds, obviously in the same direction of rotation. So her profiles are like this. Okay, but if the steam passes through the first one, he is going in the opposite direction of the second. So it has a reverser plate in the opposite direction between the 2 reed rows, just for the network to circulate and redirect the steam. Nothing else happens in this item. It's just a sine tap inverter call redirector. So he is typical in the first stage of multiplicity turbines. Like I said, another simple bias lower power stage. It provides a great drop enthalpy, which is a drop. Enthalpy is a great absorption of energy. So we have high energy steam, high enthalpy. So we want it right there in the first stage. We already do a large drop in enthalpy. to make the most of these characteristics of the steam, that it is the noblest state of steam. Okay, so we want to make a big enthalpy, and this internship provides that, including resulting in this on wheels with smaller diameters. So we return the most compact design. He can also receive the speed stage name precisely because of these aspects. In contrast, the reactor stage is the one with wheels followed by diaphragms, right? Here remember that here, before this, here we have an element of expansion, but what characterizes the Kurtz stage? There are 2 rows of pallets. Not here. Here is a wheel with a single row of reeds, a single wheel, a single disc. And along with this album there will be an expansion element, which is the diaphragm, in this case. Okay, so this is the rat stage. So there are several. Yes, I'm already here. As you can see here, it may be that this first stage be at a Kurtz stage, followed by several mouse here not here they are 2 wheels raptor, 2 smooth wheels or is it 1 wheel? Kurtz an internship. Kurtz it is a wheel with 2 rows of pallets. So that's what you have to associate and leave it at peace. This here we are just looking at people just to see if you know how to decipher a turbine. And besides that, we do have it. Simple multi-stage turbines. Then it becomes a little easier to understand. A simple internship is precisely for presenting, as I already said, a single expansion set here in case a fixed reed and a wheel. Okay, remembering that this one it's a redirector board, this one. It's the Kurtz stage. Oh, a double wheel row of reeds. No, we can't see it here if there are 2 to 2 rows. If they are a wheel with 2 rows of reeds or 2 color head cover wheel discs very beautiful. Simplicity doesn't matter either. Simple internship will be the only element of expansion with a single rotating element. It provides less rotation, lower power, more compact turbines. They are standardized by the standard, widely used for mechanically driven turbines, and it has lower efficiency too. Multi-stage turbines. Then we will see what a lot of internships, i.e. a bunch of rows of reeds, be it action or reaction, followed by 10 expansion elements of steam, then several sets expansion stages, greater power, larger turbines, obviously, and more internships. They are standardized by another API which is the standards which deal with operational conditions from them. Widely used in pure generation and also mechanical drives. It is a more efficient turbine. It is a multiple turbine stages. So that's it, simple and multiple stages. Also, I am taking a look at the time here. Leave it in the comments there if you are able to let what are you thinking, and if it is in fact being a summary, or am I going to prolong? The model starts talking and never stops. I have a bit of this defect, but anyway, that's it. I don't want to be redundant here, it's worth it. I also want to leave you with the feeling that it is a summary that summarizes nothing. So let's go. Recap, let's take a quick look. We have concepts, action and reaction turbines. We have the short stages and reactor. We have simple turbines and multiple stages, and we also have turbines condensation and counter pressure. There you will see that depending some things are easier, we obtain types of characteristics in a type of turbine from another to another type of turbine. What am I trying to say? That in a turbine, for example, condensation, it can be quite common. Find multiple turbines internships with this short stage followed by reactor stages. Okay. And it's very common to be a reaction design turbine. So there is no single feature you discriminate the turbine here. It is possible. It is necessary for us conceptualize all these aspects. Okay. Although, as I just mentioned, it does. Sometimes it becomes very intuitive, one in relation to the other, based on some details, okay? So, if I speak like a turbine, she only has a short internship. I already know what I'm talking about, a single stage turbine. A turbine of probably action, which is very difficult. Call it a reaction. Although there may also be under these conditions. Oh, I'm talking about a turbine which has 5 stages through 5 stages, he reported. It has 5 wheels, 5 diaphragms, so it is a multi-stage turbine, which could be a reaction turbine or an action turbine. It could also be condensation or counter pressure. And then you will have to enter a little more in detail. Beauty. So let's go back there for condensation and counter pressure. That's a more generic thing, right? But I had to say it like that. Is this a cat or a dog? And from this description here, what does this mean here? Let's take it easy there. When eggs are frying, the condensing turbine, already looking at the turbine, a layman perhaps. It's hard to know just by looking. Then you will see some devices there, some references to be able to decipher. But the fact is this: if the turbine it has a lower outlet pressure or discharge pressure that we usually use or escape, it's all synonymous. Okay, the pressure at the outlet is lower than atmospheric pressure. That is, we are at the exit of the turbine. This vapor is at lower pressure than atmospheric pressure. You have a vacuum inside this turbine. We're talking about pressure, turbine, condensation. That steam then it no longer has energy to be used in the process or for energy generation. Okay, so it no longer has energy considerable for use in the process. It can be applied to both drive and for power generation. Although for power generation, it's almost a rule. They are more efficient, so they have greater jump on such a peak, because it is proportional to. From the turbine inlet to the outlet, we're extracting all the steam of all the energy of that steam there. So since he's a vapor, because there was condensation, the turbine condensing is that she is transforming this vapor into condensate into water. Then she transforms literally from steam inlet to outlet. It turns everything into energy. Okay, that's what a turbine is for condensation from there, from the exhaust outlet of the turbine. It goes straight there to the condenser, almost in water. It's done. So that's the condensing turbines, is counter pressure. Counter pressure is the opposite. The pressure at the outlet it is greater than atmospheric pressure. In this case it is steam. It still has considerable energy for use in the process. So we use the energy of this steam, extract 1, generate a torque on the shaft power on that axis. Then the generator, equipment or of a driven machine, drive equipment and also the steam that comes out of the turbine exhaust. He still has energy. Have such a sink to be able to continue in the industrial process, whatever it may be, and perform other operations. We don't extract all the energy, therefore it is applied both to trigger as a generation, and it is less efficient. The smallest salt has such because we does not extract all possible energy from it by design feature. It may be that the process requires this type of turbine very applied paper and cellulose industry. The food industry there is this type of turbine. So these are the differences basics of turbine types. Let's see what else is here. Now that we've talked about it here, there's only one video giving you a little cheer. Okay, due to some complete here when the steam arrives. It's a vapor chamber so we can go into details, and then it will go through the duct. It's going to come in here, this arm he articulates to make the adjustment of the valves, as I will show later. So the steam will get in there on that flange, go through the resource pump emergency. You will fall here into this intake chamber. Go steam block, control block, intake block. Here in this case, it is the ultimate multi-stage system. Obviously, here is the bushing system, valve seats with intake box, hotline, cold part, that vapor sealing part, the first stages. I don't want to go into details, which is a summary of the staff. We're going to get through it pretty superficially. Same. The diaphragms, rotate expander plate here, extraction part, discharge housing, intermediate housing, the one in the middle of the intake box. High pressure discharge, intermediary, intermediate and low pressure. Bearing box, discharge sealing box, the side coupled. Bearing couplings, sealing system, the rings, labyrinths. And then we may with time later covering every little detail. Type of turbine of the sealing part, which is how do they start a summary, right? Just to illustrate what we've said so far, a typical multiple turbine internships, correct? That will show a little more of the bearing box, that the gear from the tachometer where the engine runs, checks the rotation, the emergency device, spherical bearings, oil sealing system. This is where the first expansion occurs, the turbine steam ring. The diaphragm I mention here is directing the steam, increasing the pressure, his speed. Here is a system that will get you steam. We can go into details more to give a greater vision, a sense of the interior of the countryside, and you only see outside, on a page any inside. Well, that's it. I don't know what you're thinking. We have it here. For those who work in an audience, intends to take to the company and want to present it to the manager. Okay, we have a course in digital format, the recorded course, which are more than each of the original content that we provide an updatable course. We will always be putting new things in there. 7-day money back guarantee for anyone interested. It didn't like it until 7 days ago to request a refund without contacts. Human interaction, it is completely on the purchasing platform and start doing it immediate start of lessons. It will be there in the video for up to a year. To get started with the certificate, we issue a certificate for you and the course also in face-to-face format. What you mean? We come to your company, a project, buy it yourself, we'll take it to you. Then we have people here. We have a team here, our partners such, and we go there, depending on the availability of each one. And we train your team. Then it starts with your manager. Then see if we are here to negotiate conditions to generate business. So, for the group of professionals, customizable content. Okay? Wow, I have a process like this. Done. I have a counter pressure machine. I have machine X, Y, Z from the manufacturer is about to activate the equipment. is my command system, which is the UTA. There is no 5. Wow, I wish you could come in a little more deep into it. I just wanted a little bit. Plus the maintenance part, we model this according to what you need. So, customizable workload, modern and updated content too. Certification is the basic scope that will depend, but at least a day of training is it's the best, there's no pain. 2 days, 3 days. It will depend on each person's operation. We can do it in groups, depending following the sequence of your roster staff. Make a class in a day or 2 days. 1 day off and do what we are here to do according to what you need. Then you can approach the project, functioning, operation and so on. Okay, gentlemen, that's it. Here are our contact details, like in the description, and there is more information, and leave a comment about what you found it there. If you liked it, we do it here with care. We wait. It's here more consistently, with more availability, more frequently. Recurrence, okay. If you can share there on our channel that people, please provide us with this information for anyone interested. That's it, and I hope you liked it. If you like it, leave a like, leave the dislike there. Thank you for your attention and patience. If you want to send a comment there, any questions, only Anderson Sales Ramen sent it here. Thanks for the participation of all. Okay, we are available there to be able to help them there, in whatever way possible. Whatever is required of us. Beauty. It cost. A hug and see you next.
Então, carga horária customizável, conteúdo, com maior frequência e recorrência, tá? Se você puder compartilhar